So let's look at what happens with those ionic compounds where electrons are transferred. So metals, we've learned, tend to give up electrons, and nonmetals tend to gain electrons. So the metals become cations, the nonmetals become anions, and the attraction between them is an ionic bond. And so in Lewis theory, what we're going to do is we're going to represent this by moving dots from one atom to another, from the metal to the nonmetal. So let's look at potassium and chlorine and see what happens when they form a bond, an ionic bond. So potassium is K, and chlorine is Cl. How many valence electrons does potassium have? 1. There's a giant periodic table on the wall behind you. How many does chlorine have? 7. It's in group 7A. If you don't like looking behind you, then you should bring a periodic table or your book or something. So both of these atoms would like to have 8 valence electrons. That's a lower energy state for them. Everything wants to go to lower energy. Or in my, happy chemistry world, they're trying to look like the cool kids. They're trying to be popular and have the right clothes, right? So chlorine needs 1 electron. So he's going around, hey, I need an electron. Anybody have an electron I could have? Could you give me an electron, please? And potassium is walking around saying, I've got this 1 electron on the outside. What's underneath? Potassium has a 4s1 electron configuration, so it's got 1 electron in the 4s. What's underneath the 4s? The n equals 3 level that's full. So he's this onion with this little bit of a layer, and if we take that layer off, then he looks beautiful and round, because that under layer is full. When you take, in fact, let's look at the, so one way to write the electron configuration for potassium is to put argon in brackets and then 4s1. So if we get rid of the 4s1, what do we have? We have the electron configuration of argon. So potassium is willing to get rid of this electron, and so he's going to give this electron to chlorine. When he gives up that electron, he gains a positive charge because he's lost one of his negative charges. And chlorine now becomes a chloride ion and has a negative charge. Now you have a positive and a negative, and they're attracted to each other. You look really good with that extra electron. And they get together, right? Any questions? Yes?
Okay, so on the other one that you did, Mg and S,
Mm-hmm.
you put 2 on Mg, but are you getting the 2 from what group they are? Or from
I'm getting the 2 from what group they're in, yes. Magnesium had 2 because it's in group 2A.
So then the other way that you showed us where you count the valence of the electrons, we don't do it like that for this one?
It would come out the same. It would give you the same result. Because magnesium's electron configuration is argon. No, not argon, sorry. Magnesium. It's neon with 3s2. Okay? And so there's the 2. So for magnesium would want to get rid of those 2 electrons and become a 2+ ion. Okay? Any other questions? That's a good question. So in that drawing we did, the chloride ion has an octet. The potassium ion looks like it doesn't have anything, right? It lost its only valence electron, but it still has all of those core electrons. When you lose all the valence electrons, then the highest level of the core electrons becomes the new valence electrons. I think the reason that we don't draw those, because a student asked yesterday, well, why don't we show the potassium ion with 8 valence electrons? Well, we don't want to be bringing dots in the Lewis structures. It would get very confusing, because here we had 5 dots, and now all of a sudden we have 8 dots. And where did those dots come from? Well, they're from the core electrons. No, we're only looking at the original valence electrons. So when a metal loses its valence electrons, in the Lewis structure it looks like it doesn't have any valence electrons, but what it does is we peeled off that incomplete layer on the outside, and then underneath is the noble gas configuration. Okay, we indicate charges on ions. So on the cations, they're going to end up with no dots, and you just put their positive charge, 2 plus, 1 plus, whatever. For the anions, we put brackets because they're going to have 8 valence electrons. They're going to have 8 dots around them, and so we put brackets around them like I did in the previous slide with the charge in the upper corner on the outside. Now this is important, so I'm probably going to get some questions about this. In mastering chemistry, the charges are shown, but the brackets are not shown. Please do not text me and ask me how to make brackets. It doesn't do brackets, okay? It does want you to show the charge, but it just doesn't do brackets. I don't know why, but it doesn't, okay? When you're doing it on paper, though, put brackets. So let's look at the Lewis structure for the compound sodium bromide. So sodium is Na, and bromine is Br. How many valence electrons does sodium have? 1. How many valence electrons does bromine have? 7. So can you see how these two could get together and help each other out? The sodium wants to get rid of that electron. The bromine wants another electron. So the sodium gives its electron to the bromine. Now sodium has a positive charge, and bromine is bromide with a negative charge. So that's illustrating, I didn't leave much room. If we were going to do it without all the messiness, we'll do it like this. Lewis structure can help us to predict formulas. So let's do the Lewis structure for BaF2 and see how this works with something a little more complicated. So barium, what color do I have going on here? Barium is Ba, and how many valence electrons does barium have? 2, thank you. Barium has 2. And the other compound we have here is fluorine, and fluorine has 7 valence electrons. And so we saw in a previous example how fluorine can get some help from a metal. The metal can say, okay, well, actually I don't want to do that one, I want to do this one. Barium can say, well, okay, I'll give you this electron. And then fluorine's all happy, and fluorine becomes a negative anion. And now barium has a +1 charge. But is barium happy? No, barium still has 1 more electron, and this fluoride ion is not willing to take it because that would mess it up. So what barium needs to do is it needs to not find another fluorine. So here's another fluorine, and this one also has 7 valence electrons. And the barium can give this other electron to this fluorine. That becomes fluoride. And now the barium has a 2+ charge. We learned how to do this back in chapter 5 just by following some rules. And now we're understanding why. Why does it do this? Well, barium has 2 valence electrons and it needs to get rid of them. Each fluorine will only take 1. And so there needs to be 2 fluorines to accept the 2 valence electrons from the other one. Is that nice? Your battery is running low. You might want to plug in your PC. So we got juice to the PC. We're good now. Any questions about that example? It's all about sharing and cooperating and everybody getting what they want. Yes?
They're always trying to get they're always trying to get the first element.
The first element in these ionic compounds will always be a metal. And they're going to have 1, 2, or 3 valence electrons. The shortest, easiest way for them to get 8 is to lose those instead of gaining more. For the nonmetals, they're already pretty close. They've got 5, 6, or 7 valence electrons, and so it's shorter for them, easier to gain to get to 8 instead of losing to get down to the next level. Good question. Any other questions? Question, what on earth is this doing? I don't know what's doing. Here's another example. Use Lewis theory to predict the formula of the compound that forms between magnesium and nitrogen. In the last one, they gave us the formula. Here, they just give us 2 elements and ask us to predict the formula. Well, we're going to look at their Lewis structures. So magnesium is Mg, and nitrogen is N. So I want him a little closer. How many valence electrons does magnesium have? 2. 1, 2. How many does nitrogen have? 5. 1, 2, 3, 4, 5. Okay, so how can these guys help each other out? Well, magnesium can donate this electron to the nitrogen, and it can donate this electron to the nitrogen. Now this has a 2+ charge, and the nitrogen's got a 2- charge, but is the nitrogen satisfied? No. Magnesium's good. Magnesium says, hey, thanks. See, I'm good now. And the nitrogen's like, wait a minute, I need another electron. So we have to bring in another magnesium. So we'll bring in another magnesium with 2 valence electrons. And this magnesium can give 1 to that nitrogen. Now this nitrogen has a 3- charge. The nitrogen's happy. Is the magnesium happy? No. The magnesium still has an electron. Okay, so what do? Well, let's bring in another nitrogen. So here's another nitrogen. 5 valence electrons. This magnesium gives its other valence electron to the nitrogen, and now he's got a 2+ charge, and he's good. But the nitrogen's not good. This reminds me of my Grandma Johnson. My Grandma Johnson was overweight. Let's just be honest. She's been dead a long time, so she won't be offended. It was just plain true. So she liked to eat. And I remember very distinctly at dinner, we'd have bread and then, like honey or jam or something, and whatever it was, she called it with it. So there was bread and with it. And so she'd take a roll and she'd take some strawberry jam, and she'd put the jam on the bread and eat it, but then she had a little bit of jam left, so she'd have to take another roll. And she'd put the jam on the roll, but there wasn't quite enough jam. So then she'd have to take more jam, and then she'd eat the roll, and there'd be jam left. And she could go on eating bread and with it until you thought she was going to explode. And that's kind of what it feels like here, doesn't it? It's like we had the magnesium and the nitrogen, and that wasn't enough, so we took another magnesium, and that was good, but then we need another nitrogen, and now we need another magnesium, and is it ever going to end? Eventually, it comes out even. Or you run on a bread, right? Okay, so the magnesium, sorry, my brain does that. The magnesium there is happy, the nitrogen isn't, so we need to bring in another magnesium. Another piece of bread, and this one has 2 valence electrons. And so we take these valence electrons and we give them to nitrogen. We give this one to nitrogen, and oh look, we finally came out even. So this is -3, and this is 2+. And it took 3 magnesiums and 2 nitrogens, but everybody's happy now. Okay. They shared their dots. Well, they didn't really share it. They weren't sharing. I shouldn't use that word. They transferred their dots until everybody was happy. Yes?
Is that why it's negative and not just regular negative?
Yes. The other ones were like bromine, which only needed 1 more electron. And so it gained 1 electron.
Whatever you add, you put
Each time you add an electron that it got from someone else, the number of protons doesn't change. So the charge becomes negative. You add 1 electron, you have a -1 charge. You add 2 electrons, you have a -2. You add 3, you have a -3. So what's the formula? That's what it's asking. Well, count them up. We've got 1, 2, 3 magnesiums. So Mg3, and we've got 2 nitrogens. Mg3 and 2. We learned how to come about this formula in a different way in Chapter 5. Now we're looking at what's going on with the electrons. What we did before is we learned from the periodic table that magnesium was 2+, and that nitrogen was 3-, although we didn't really understand why. And then we did that crisscross thing, and we came up with the same formula. But this model is helping us to explain why it does that. Any questions?